welcome back. So now the next talk is a perspective talk, and it will be delivered by Professor Saswata Bhattacharya. So he is an associate professor in Physics Department of IT Delhi, Indian Institute of Technology, Delhi. He did his PhD from ICS in 2011. Then he went for a postdoc of 4 years at Institute, Berlin. And after that, in 2015, he joined IIT Delhi as an assistant professor. And he has received a number of awards. To name a few, he got Young Achievement Award by Department of Atomic Energy, Early Career Faculty Award by IIT Delhi. And his research interests are in density functional theory approaches to predict properties of materials such as which are applied in basically heterogeneous photocatalysis, solar cells, storage devices, etc. And today he'll be talking about probing excited states in materials, benchmarking hybrid DFT versus GW versus BSE versus model BSE. So, please.
So thank you very much for the kind introduction. I'm honestly feeling before I start, it's a very nostalgic for me because I was here in ICS, I was doing PhD, and I used to come here plenty of times to attend lectures about Abhishek Mukherjee. So from that perspective, I am really recollecting those memories, and today is basically getting invitation from some of my professors like Professor Indra Gupta. It's really very nice. I mean, also Manaranjan. He's my colleague, but I mean, I did class of Professor Indra Gupta, and whatever DFT I've learned is basically from him. So when he invited me, it was really, really very precious for me. Okay, so let us get back to this talk. So you have done a lot of very heavy equations since from the morning. So that's why I tried to make things rather simpler. So which one is the point? So even though this is still the same thing like GW, BSE, model BSE, lots of complicated things, but I will not go directly into these complicated things right from the beginning. So I decided like about 70% I will talk about how you can deal with optical excitations and excited states, and remaining 70%, remaining 30% is something other things. So we are interested on materials, and I will try to show how you can address excited states of materials in a meaningful way. So there are various things that we are doing in my group. So this is exactly the area that I'm going to focus today. So that is excited states in materials. But in general, once you talk about materials, it is not about only understanding the excited state. There are many other aspects which are also equally important. For example, so let me just very briefly tell you, suppose this is the material, and you are trying to understand this material in an experiment. So whenever you have this, so this material is usually surrounded by some ligands, like it can be oxygen environment, it can be hydrogen environment, it can be argon environment. And then inevitably this material will not remain idle. It will exchange atoms with this, and it will form different types of structures. That's obvious. That's kind of the defects, or there are really many things like defects or interstitials or other things. So the first part, or the important part, once you try to understand materials property, is what is the structure, and then again, after knowing the structure, what are the most stable phases? So if you know it very clearly that what are the structures and what are the most stable phases, then only it makes sense to understand the electronic structure and the excited state and other things. So in this talk, I will not talk about this part, that is the structure and the most stable phase, but I am here until tomorrow evening. So if any of you are interested, you can talk, because there are lots of interesting things that happens over there, especially many times your harmonic approach does not work, and materials are very much sensitive to anharmonic effects and other things. So this is also, and also understanding structure is also very important thing. It's not very straightforward. You have to do some. I've done a lot of development in understanding structures using genetic algorithm and other methodologies. So anyways, and also in the next month, I'm going to talk extensively on this in ISAs in one of another conference organized by Saswata. So if some of you are attending that, then we will meet again and we will talk about. So let's focus on this. That assume that I know structure of the material by some means, be it from experiment, be it from my own development or theoretical perspective. And once I know how I can understand the electronic structure of the excitant. And typically we are talking about, okay, so usually I follow a strategy like this. So I try to understand so this is the problem once you change from a Mac to Windows machine, I cannot help it. Everything was very nice in my computer, but somehow it is not like here. So anyway, so I try to understand the structure. If you do not have experimental support, say genetic algorithm methodology, this gives me all the microscopic details of the material, and then I can understand the free energy using the atomistic thermodynamics methods, where we do use harmonic approximations. But if you want to know beyond to capture anemonic effects, you can do thermodynamic integrations and other methods also. So this helps me to get all the macroscopic details of the material. And once I get to know that, then only I do DFT and beyond DFT methods to understand the excited state property. That's typically the idea. And I'm not going to talk about this part. I'm only going to focus this part here in this particular presentation. But typically, once you talk about simulating a material which is absolutely unknown, so in principle, you should focus into all these things. And that's sort of the idea. Okay. So we are talking about semiconductor mostly. And semiconductor means you have a gap and we have to probe this valence band top and conduction band minima in a very accurate way. And usually, I have taken two very simple systems in this particular talk. One is very well known TiO2. Most of you are familiar with TiO2 if you are working on, say, materials, oxides, and these things. It's a very simple material, but it has a pretty high band gap, so there is no visible light absorption. Now, to do that, and to help it for visible light absorption, what we usually do, we make defects. And then the question comes that how you can determine the defect level very accurately. So if we are talking about applying this TiO2 for, say, photocatalysis, then situation is like this. So these are the HER and OER level. You have to somehow do something, make a defect state so that this comes down, this comes up, and this requires accurate estimation of these levels. So that's how I will later on recollect how GW and BSc really help you to get into that. But anyway, before that, let us try to understand that how the defect level are there. For example, if you make if you dope the system and if your defect level comes here, it's not good because it will really make things worse because it is basically a mid-gap state. It will help the electron hole get recombined over there. So that's not what we're talking about. What you need to do actually, you need to make your defect state here or here so that the gap is getting shortened as well as this is not in between. Now, if it is so, then it is good for photocatalysis. But if it is not like that, instead of that, if it is like that, then also it is not bad. It may not be good for photocatalysis, but it can be good for optical applications. So here we are talking about these. So TiO2, the kind of dopants I will do, so those will make the defect level come here. But if you want it for photocatalysis, then it has to be like this. So if you are interested, you can see these references. So this type of co-dopant can make it good for photocatalysis, but I'm not going to talk about this in this particular presentation. So we are going to talk about some of that. Now, so let us first try to understand what is the challenge if you want to accurately estimate the valence band top and the conduction band minima, because the moment you add a defect into a, or you add some atom into a material, the problem is that you have to make the defect to be localized. And this requires you have to expand the supercell. reasonably big so that you can get a flat band like this. And this makes things really computationally expensive because if you are doing GGA, that's not a big deal. But if you are doing higher level of theory, if you have a bigger supercell with a lot of atoms, your defect is localized, but you cannot do it computationally so easy. So this is exactly what this is the defect. This is some add atoms here. I have used a non-metal, for example, and this is a quite big supercell. We got a flat band, that's good, but the point is that's computationally expensive. Now let us see whether how good is our normal DFT to address this problem. Now what I did is the following. So we calculated the defect charging energy or defect formation energy. So the total energy of the defect at a charged state, then the total energy of the pristine system at a neutral state, chemical potential of the defects, and the chemical potential of electron, which is typically all about Fermi energy. So we are varying this chemical potential of electron from valence band top to conduction band bottom, and we can see that how the defect is getting stabilized. Now, if you do it at the level of PPE, and if you plot the formation energy here, then you see once you are talking about a p-type dopant up to this, the +2 charge state is the most stable one. But later on, once you are talking about an n-type dopant, -2 charge state is the most stable. To do the same with, say, KC, then -2 is not at all stable. It is all over +2. So there is a discrepancy clear.
Just increase the gap in the two cases.
No, that's the same.
When you're doing this, you get the experimental gap.
Yeah, I can explain.
That's right.
Yeah. Otherwise, yeah, I can always.
No, but some people also correct for the, like, because I mean, basically there are corrections for these levels also when you're changing your gap from your theoretical to this one.
Yeah, that's true. But here I did not do it. I took the experimental gap and I also aligned the valence band top very accurately with more sophisticated calculations. So now what I tried to do, that can we really fix up, because of course with GGA the band is hugely underestimated, and that's why can you really fix it by applying U? By applying U, you can fix the band gap, but you cannot fix the energy. So now during morning lecture, somebody was asking to Manish that can you do it better with meta GGA or things? I would say that you can make things possibly better, but not here. So that does mean that this material, and then why it is happening, because it's an oxide system. If you simply calculate the oxidation of oxygen molecule binding energy, you can see because of the self interaction error, there is a 1 eV discrepancy from the experimental binding energy and the actual binding energy, and that's why this is definitely going to happen. So fine. Now, so what we did is that then first we tried to understand that what type of defects are specific defects. We just determine different type of non-metal defects, like these are all, this is substitution, this is interstitial, this is substitution and interstitial together. And then we tried to understand that, okay, what are the defects which are stable, and we plotted this type of diagrams and we showed that, okay, the non-metal defects, substitutional defects are overall stable. And like for nitrogen, carbon, sulfur, selenium, all these are more or less stable defects. And then we try to understand that, okay, now what happens once we try to understand the exact state property of this type of defects. Now, if you plot a simple, say, configurational coordinate type of diagram to understand that the emission, I mean, how much is the width, and then you can clearly see that, so these are all falling within the visible region, but not phosphorus. So fine, at least to get the information that these are sulfur, carbon, nitrogen, selenium. If you go TiO2 with this type of substitutions, then you can get visible light response for optoelectric applications.
What is this configuration called?
So what I did is basically that this is -1 charge, this is 0 charge.
What is the coordinate?
So coordinate is basically how we charge the atoms are getting relaxed. So
It's like central type, whatever atom, and then with
yes,
respect to that.
exactly. So basically this is the formation energy, this is formation energy, and this is the geometry with -1, this is the geometry with 0. and then and then also we did with what, with -2, and then that way you can calculate how much is the vertical detachment energy once it was. So so anyway, now the point is that now this is nothing to do with the optical properties. This is just to give you the typical estimation that with visible light will it be working or not. Now, if you want to understand the optical properties, you cannot do it within this framework. And let us very briefly try to understand, though we have enough lecture on this morning. So what happens is that if you try to understand the excitation, the problem is here. So in DSP, you have a typical interacting system, and you mimic this interacting system with a completely non-interacting system, ensuring that they have the same density. That's very nice. That works very good, but at the cost of losing the interpretability of this eigenstates. So that's what I think now you all are convinced that this is fine. You can talk about the ground state, but you lose the interpretability of these eigenstates and other eigenstates. So if you want to understand that, you have to go one level up of this ladder. So that's typically what you do. You shine light, you eject electron from the valence band top. Then this is how you can probe the valence band top. So and this is basically the photoemission experiment. That's exactly what. If you do the inverse, that is the inverse photoemission experiment, if you bring one electron in the conduction band, this is shine light. That's how you can probe the conduction band. Now, if you do both the things simultaneously, then you can, in principle, calculate the fundamental gap. That is the EG, which is basically the difference between ionization and light. So that's what you have learned in this morning also. But still, it is not good enough to give you the idea about the spectra. So if you want to understand spectra, then you have to go even one level up. But before that, let us see how you do that. You do it using this many-body perturbation theories, using JW approximation. So that's typically the first particle. And this is your self-energy operator. So you start with the quantum eigenstate that you get here, and then you update essentially this with iterations. Now, this is Manish's picture was much better with the horse, with all these things, but the idea is kind of similar. So you shine light, and then you create a hole there, and then this hole creates kind of time-dependent polarization due to creation of hole, and then it will get screened with the electrons, and you really need to take into account. That's part of the idea. So that's basically the dynamical scaling of hole for the formation of the first particle, and this is the W of sort of the GW. So this is what we have seen. And then it is typically a light matter interaction. So you can write down your polarizability like this. These are all different terms. You truncate everything at the first order. You can, in principle, calculate all these properties. So anyway, so let's not go much detail because this is not the intention. But if you want to understand the spectra, so then what you do is somewhat like this. You again shine light, but not as much energy as you did in the previous case, so that this goes here and they form a bound state. Now the idea is that you have to calculate this electron hole bound state, and this comes under Bhattacharya equations that was in the formal lecture. So here you have this electron Hamiltonian. This is basically a two-particle Hamiltonian, electron hole and electron hole. So that's what you typically need to calculate. So anyway, so once you do it, and if I get back to the TiO2 problem, so then you see in this previous slide, so here this starting point is very important because that's what you take from the construct. So if your starting point is a crack, so then even if you do GW, then you cannot really correct it in a very precise way. So that thing one need to keep it in mind because we are not doing self-consistent GW, we are doing single shot GW. So if you are doing single shot GW, so your starting point is extremely important. That's what you are taking up. So now you see, so the static real part of dielectric function for this pristine TiO2, experimental value is 5.62. If you calculate it with PBE, it comes out 6.88. If you calculate with HSE, it is 5.1. So obviously, you can understand that if you want to correct it, this is basically the better compared to PB. So if you do it with PB on top, if you do GW on top of PB, you will not end up getting a correct result. So it is more logical to do it on top of this. And that's exactly what it is. And then if you do that, so that's exactly what we did to validate our starting point for TiO2 system. So we did BAC on top of GW on top of HSCO6, and you see that there is excellent match with the experiment with this here. So and then if you want to converge the orbitals, so you see here you can clearly get the sharp excitonic peak, which Manish has shown many times in his presentations also, that you should have a very, very sharp excitonic peak. So it is, and also if you do simple GW, you will not get this type of excitonic. So anyway, so I hope I have convinced you that this is sort of, I have validated my functional, so that I need to do it on top of HSCO6. I should not do it on top of PB because the starting point is not good. And then I do not need to do self-consistent GW because single sort is sufficient to do these things. Now I get back to my dope system where I do not have any experimental data. Yes, if you have fun. No. So then this is sort of okay. This is also the situation. So your HSC is basically reproducing somewhat like this. If you do GW, sorry, just a minute. So this is HSC for TiO2. This is GW, and this is BSC on top of GW, and you see this excitonic peak is very much there. And then if you compare with experiment, you see that there is a very nice match with the experiment, and you can clearly see that all this this is E parallel to X, this is Y, and this is E parallel to Z. So that's how that for TiO2 system, this is how it should be done. Now let us come to the dope system, because I have validated my functional very clearly for the piston system. So once we do that, then there are certain things which are really interesting. For example, you see that once you have S dope TiO2 and AC dope TiO2, if you are doing BSC, you can clearly see in the visible region there is optical anisotropy. For example, this is not responsive in the Z direction, but this is very much responsive in the X and Y directions. But if you are doing it the same thing with a simple DFT, you will not end up getting this optical anisotropy. Now, why it is so? If you try to understand this is optically active along X and Y directions, and it's optically inactive in the state. So if you simply plot the density of states, you can clearly understand why it is so. So this is sort of the pristine system, and once you make the defect, then the defect state is lying here, and these are P-type dopant. And if you plot the orbitals, you see here, so these are the XY orbitals, so Px and Py. These are contributing close to the Fermi energy, and the Z orbital little bit shifted, so that's why obviously the Z will not take part in the optical transitions, and that's nothing unusual. So this is what the situation. But if you go for nitrogen and carbon dope TiO2, then the situation is this is optically active in all these directions. So there is no anisotropy, and that's kind of obvious because here also if you plot the same thing, so these are N-type dopants. So that's why the defect state is more towards conduction band, and you can clearly see that here X, Y, Z, all three orbitals are contributing, and that's when this is optically active in all these directions. So anyway, so now, so the idea is that this is sort of the take-home message out of this is that if you do not do GW or BSC, you cannot really capture this information because the peaks get shifted, and there is definitely that it's absolutely wrong from PP or this type of thing. But this is not the only reason why we need to do many more perturbation theory. There is much more into that, especially if you want to understand the excitons. So now I will switch gear to something little bit different problem. That's hybrid perovskite, hybrid perovskites, and there this material is humongously useful for solar cell materials, And if you want to understand solar cell materials, then you need to really understand how the excitons are formed, what are their lifetime. Yes.
Just before you come to this part, can I ask
Yes,
you a question?
sure, sure.
So you essentially you have the GW, all your eigenfunctions, and on that you just you introduce this electron hole interaction term. Is that the way it
Yes.
is done, the BSE?
Yes. So first I have my quantum orbital, that is HSCOC. I correct it with GW, and on top of that I correct it with this. Basically electron hole interaction. So two particles. We do not take it usually.
So you're using the GW wave functions for the.
Yes. And then on top of that I correct it with this. Yes.
So done in the diagonal approximation.
Yes.
So basically the HC orbitals which are made normally.
Yes, that's true.
Is there a, so in these systems there is also this thing about polarons, right?
Yes, I will, but here I did not talk about much of polarons. I will come extensively polarons and exciton in my next part, because this is what I created for students. Since from the first slide, if I talk about polaron and exciton, they will go crazy. So now polarons and exciton, all these things will come. Yes. Okay. So first it is like this. Let me go back. No. So this is my density of states. This is my Fermi energy. So the moment I make a defect, Fermi energy gets changed. I realign again at 0, and then this is my defect. Of course, the Fermi energy in the pristine system and the Fermi energy in the defect system are different, but I'm aligning both at 0 so that I can compare where.
It's a roughly new system.
Yes, yes. Because number of electrons are different. So obviously that it is N type and sometimes it is P type, depending on whether it is giving electron to the system or taking out. Okay, so very briefly, why these perovskites are interesting? Because you see that we usually know silicon world, that is very, very interesting. And if you go to IIT, you will see all this silicon all over at the roof.
But here also.
Okay, yeah.
And you saw them in our campus.
But the idea is that they are very, very expensive, and IIT or SMGOs, they are rich institutes, they can afford that, but we cannot afford it at our home. But we cannot afford it at our home. So that's why we need to aim always something cheaper. And that's why we introduced the organic world. It is inexpensive and also fine, but it's very inefficient. So that's why the idea is that can we make some synergy of both the worlds, that inorganic, this is organic. And if we can do, then we can get the best out of that. And that's also sort of the idea that if you try to make a flexible screen like this, because as you see that many of you have iPhone, but you are very much scared that if it is dropped or something like that, then you will go crazy, you will drop 1 lakh or something like that. But instead of that, if you get a flexible screen like that, even if you drop it, it doesn't matter. So that's why this field is ever growing and understanding, and this type of screen was already introduced in one of the Olympics by Samsung. So that's quite coming up. So the idea is that you have to make somehow the situation of this world, the silicon or the GAN world, this is the organic world. Now, if you want to make materials, so typically, what is the challenge? The challenge is, once we are talking about the inorganic world, it is all about crystals. And once you talk about the organic world, these are all about molecules. Now, the first challenge is that what happens at the interface? So once you bring two worlds together, there is new material at the interface. Of course, you have to understand their optical properties, like we did. So this is a simple MOS2 monolayer. This is another material. This is ion group, and this material just conducts electron very heavily, IV characteristics. If you plot experimental, you will see this. But I'm not interested into that. What I'm talking about is something different. The material is like the organic comes inside this inorganic material and it continues. So this type of material is really interesting. And one such material is very well known, which is lead halide peroxide. That's called MAPBI. So if you just Google, you will see plenty of works are going on this material. And it's a very simple material. But even though it looks very simple, the material itself is not very simple. Let us try to understand. So it has the experimental band gap in this region. And if you try to calculate it using PBE, for example, you actually match pretty well. Now, if something is matching, then we usually get encouraged that, okay, if it's matching very well, then we should do it. I mean, there is no point to go beyond AFT or something like that. But somehow, sometimes we need to ask that even if it's matching, why it is matching? Because this material is containing lead and it has a lot of electrons. So in principle, there should be spin-orbit interaction. So if you include spin-orbit interactions, the band gap is humongously underestimated. It's coming to 0.49. That's absolutely absurd. And then also you will see that, okay, this material is containing lead, iodine. So there should be electron self-interaction error. So how come PB can take into care of all those things? If you include only self-interactions error using HSC, then you overestimate the band. So you see, once you include the SOC, you underestimate everything. Once you include the self-interaction, you overestimate anything. And once you do not include any of this, neither SOC nor interaction, you somehow accidentally end up getting the correct result just because they actually cancel out each other. So that's what it is. But that doesn't mean that you need to do it without including it. Now, if you want to make things better by tuning the alpha parameter of HSCO6, you can somehow make things like this. But if you want to make things even better, then you add GW on top of this, you get this, but still the exciton feature is not there. That comes once you add PSC on top of this, then only you get everything absolutely correct. So the idea is that so you start from here and you end up here. From number wise, you do not improve much because you can see that if you compute the number of CPU hours you need to invest to get this number, this number, there is no comparison. And if you say that, okay, this is 1.54, this is 1.57, and this is 1.63, why should I do that? That comes here. So once you are doing PPE without SOC, this is basically your levels. So that's your conduction band bottom, and this is your valence band top, and this is your band gap. The moment you include SOC, this gets splitted and it comes down, and everything is hugely underestimated. The moment you include the self-interaction error, the BPM comes down and you overestimate everything. And the moment you include both, then you end up these things. Now, what is the thing that we need to really take into account? That these levels are very different that you have in your conscience compared to with better advanced theory. So that does mean that if you are trying to understand the stability or the exciton or other things, then these levels makes much more sense compared to these.
Would you align it?
What is the reference?
Reference is so this is no, actually reference means what do you mean?
So you have to, so these are all offset, right? So you have to put something with respect to some, like, so
So
typically
with respect to backward.
so there's a surface,
Yes,
surface, and
yes,
you have to align it
yes,
to the
exactly.
vacuum levels. And
So once you calculate the work function, so you basically take a graph and then you align. So that's what the idea. Okay, so now if I go back to this material, a bit of brief that this material contains lead. Lead is toxic, that you know very well. So somehow you have to get rid of lead. So how you can get rid of lead? That's sort of the real challenge in this material. So people are trying to do different types of substitutions like SN or GA or this type of things. We also did some things like that. But the problem is that even if you do it, you can somehow improve the absorption efficiency or something like that. But that's not very meaningful because once you substitute, it will always come with some lead vacancy. And this late vacancy will always create a mid-gap state. And if you have some such type of mid-gap state, so it will act as electron hole recombined center and it will degrade the solar cell performance. So that's what it is. So we are not much interested into substitution of lead with something else. So what we did is that we followed two strategies. So one way is, let's go for a double perovskite, so that you start with A PP X3 to A PV1 B3 X6. So we just doubled it, and this PB is replaced, the double valence PB is replaced with single valence and triple valence. So that's sort of the idea of a double perovskite. And then we try to see whether double perovskite is serving the purpose for a solar cell application somehow. The other one is to go a completely different materials, so that's called chalcogenide perovskite. So I will also try to see how the chalcogenide perovskites are performing in terms of solar cell applications. But so far so on, I did not talk much about the exciton, so this will come just in few minutes. So the first thing is that once you go with the conventional experimentally synthesized double perovskites, so these are the two materials which are experimentally synthesized, and there is no visible light response. That's sort of not good. So if you do not have it, what you need to do is basically that these are all possibilities from the periodic table, and if you can do high throughput kind of methodology to really screen materials which can serve our purpose to get a visible light response. So what we did is the following. We did high throughput screening from first principles. Then we started with EFT with semi-local, that is PP, very, very good. Then we screened based on PP. Then after the best from PP, we screened with HSE plus SOC. The best from HSE plus SOC are taken care of with GW on top of HSE plus SOC. And then we proposed the following materials that, okay, if you substitute with these materials, so then maybe they can serve the purpose to give you visible light response. And later on, we also experimentally synthesized this type of material with our collaborator, that the prediction that we did from this high throughput screening is really working. And it has to be, because GW is pretty accurate methodology, and then these all materials are experimentally synthesized. But now comes the other parts. So this is fine. These are one sort of understanding the band gap and commenting whether the band gap is falling in the visible region or not. But that is not enough to comment whether the material is good for solar cell or not. If you want to do that, you need to go much beyond. You need to understand its exciton binding energy, exciton lifetime, exciton radius, and also you need to understand the electron phonon interaction. So these are a few things, and these are few methods that I'm talking about, because the point is, even though GW and BSC are really good, but for a real system, many times, if you have a large supercell, you cannot really convert BSC. So if it is not that, then what is the alternative? That's exactly what I'm going to talk in the next few minutes. So how much time do I have?
Start with that. 3:45 it starts, right? So you started 5 minutes later.
10 minutes, 15 minutes like that. Okay, perfect. So this is sort of that if you want to understand the band gap, then you can calculate it from GW. So that's basically the difference between your IP, this is minus electron affinity. And then if you want to understand this bound state of the electron and hole, then you need to do it within BSC. So that's what it is. But here there are additional factors which are also very important, and one has to understand them. So how it is so? So once this electron moves from here to here, then they are basically kind of free. And then this electron cools down, and then here the exciton forms. Now in between here, this may also create a polaron. Now here there is a competition. the binding energy between the polaron vis-a-vis the binding energy of the exciton. And neither of them should be very strong. So if it is optimal for either case, then only the material will be good for conducting current. That's what it is. And there you need to understand that how this electron is actually interacting with the lattice vibrations. So that comes at the electron phonon interaction. So you need to understand that also. But so far so on, there is no very direct way to capture this electron phonon interaction. There are classical methods that I will talk about, but not a very well-established quantum mechanical methods or something. We are presently developing some methodology with, for example, there are Praxis group in Cambridge University, but so far so on, it is under preparation. So anyway, so for this set of double perovskites, if we calculate these electron phonon interactions, so the point is that this coupling is pretty high. And as a matter of fact, if you compute the polaron mobility, that's also pretty low. So that's why this material may be good for optoelectronic applications, but not very good for solar. Because this polaron mobility should be pretty high. If you compare it with respect to the normal MAPBI3 material or something like that, then these numbers are very, very low. So that's sort of the problem and how you can sort of tune these electron phonon interactions. I mean, that's the next level of challenge. Yes.
Skin material. How much time does it take to perform the calculation? Also, you mean, right? Is it experiment?
Yes.
0.0.
Yes. It takes, supercells are very big. I mean, it takes humongous amount of hours. I'm very thankful to my students. They have enough patience to do such calculations. It takes a lot of time. I mean, I would say, this supercells typically contains 40 to 80 atoms, and it requires nearly 300 to 400 processors for more than a week to convert one. Typically.
There is any problem?
Yeah. If there is any problem, then again you have to do, because the convergence is always a big source.
Alpha E, what is alpha E?
It's electron phonon coupling constant.
So this is a milli E. I'm trying to understand.
Yes, it's basically.
I see. It's okay.
Yeah. So if you have a question, you can ask. So, okay, so that's what the idea is. That so now that's why I switch from double perovskite to another class of material, that's chalcogenide perovskite. These are also recently synthesized material and pretty promising as far as experimental perspective. But I do not think that they are very good, because once we did it, we found that the exciton binding energy EB is larger than that of conventional halide perovskites. We also observed, by computing the electron phonon coupling parameters, a more stable charge-separated polarized state as compared to that of bounded cells. That's typically the problem that I was talking about, that there is a polaronic binding energy vis-a-vis the excitonic binding energy, and if both of them are not optimal, it does not work. So anyway, still, if you want to see the numbers, so these are sort of the exciton binding energies, and these are the electron phonon coupling constant. If you compare it with double perovskite, they are already falling in the same range. So that's why we do not say it is very good, and the polaron mobility is also not at all good for this class of materials also. So even though maybe they are good for optoelectronic device applications, but not for solar cell. I mean, to be very honest, at least from these numbers.
So what is the upper and the lower bound?
Yes, so that comes from the 1 year mod. So actually, sometimes you cannot convert DSC. So what you need to do is that you apply 1 year mod theory, and there is a dielectric constant E. So that contains two contributions. One is the electronic part. This one is the ionic part. So if the ionic part is dominant, so then you get the lower bound, and if the electronic part is dominant, you get the upper bound. Now, if you have the experimental dielectric constant from experiment, and then you can put it over there and you can compute the actual exciton binding energy. But many times experiments are not available, so you need to do it this way, even if you do not able to do BSc straightforward. So I will show it one example. These are the materials that is not good, and then I will come up with the solution that which are the materials which are good, and then how you can do that. So this is one class of chalcogenide perovskite. So if you want to change material and then if you bring hafnium and all other things, then also situations are possibly improved, but not very improved. So I'm not much bothered on that. So this material is also good, but still the numbers are somehow slightly improved, not drastically improved. So that's why what we did is that we went to two-dimensional perovskites, and we tried to see that, okay, what is happening for two-dimensional perovskite, because once you have a 2D structure, the physics is very different and the expressions are different, and usually they should have a better mobility and similar. So here, so this is called the Rudelston buffer phase. So this is n equal to 1 because we have one layer. Now if you go to n equal to 2, so this is n equal to 2, you have 2 layers, then this is 3 layers, and this is n equal to infinity. So in this type of material, these are very, I mean, also we have experimentally synthesized also this type of material with our experimental colleagues, and they are very promising to be very precise. But the problem is that in these materials, doing GW is very difficult, because if you are talking about only n equal to 1, this contains nearly 30 atoms, or maybe slightly less than 30 atoms. But the moment you go to n equal to 2 or 3, then the number of atoms is so high, you cannot do precise GW or BSc calculations. And that's exactly you end up getting. So once you try to convert your number of empty bands, your this peak keeps on getting shifted. And also once you are trying to do the same thing with reasonable amount of K points, so then also your this peak keeps on getting shifted. So you cannot convert your BSc in any meaningful way. So that's sort of the problem. And if you do not get it, you cannot calculate the exciton binding energy by taking the difference of the GW vis-a-vis BSc peak to really compute. So then what we did is the following. We did little bit trick here. So that's sort of the self-energy operator, and this looks like this. Now here you have this epsilon. We replace it with an analytical function, which looks like that. And this is basically the ion clamped dielectric function. We can calculate it from the functional perturbation theory. And this is where you have an unknown parameter lambda. What we do is that we fit it with GW calculations and then compute it here. So that's called model BSc. So basically we are not doing exactly the BSc, because doing BSc is not possible. You can see that even after this, you cannot increase the K point. It is not possible that the peak is keeping on shifting and shifting. You are not getting able to convert your BSc kernel. And as a matter of fact, after a certain number of CPU hours, even if you have access of CPU hours, it is not going to work. I mean, the job will get truncated because of the memory problem and other. So from there, what we do is the following. This one we replace with an analytical function which looks like this. This one we compute with the functional perturbation theory, and this lambda we calculate it from here. So this is what we plotted using GW, and this is what we have fitted, and that's how we compute lambda current. And then if you put it back there, that's how you can convert this peak. The difference between the two shiftings is very small, and we can show here that this is the BSc and this is the MBSc. The accuracy of both for n equal to 1 is very good. But for n equal to 2, 3, 4, and so on, you cannot do it with using BSc. So there, your MBSc works very well. So that's what the typical idea. And you can see that there is no cost of accuracy once we talk about the first peak. Yes.
Just a clarification.
Yeah.
Your blue curve is always above the other curve, yellow curve. Is that? Should there be some kind of some rule that I'm just surprised that it is always above. So
that maybe if it is for this system, But in principle, I don't think that there should be any reason. Is there any?
I don't know. That's what
Yeah.
I think. I mean, the peak positions lined up that
Mhm.
ecosystem, but it just looks like all of it is shifted up.
That might be. That's a good point. No, but here it is coming down. That's I think there is no.
It's just that in the range that you
Yeah.
plotted, maybe that's what.
Exactly. I mean, if I plot it for the entire length. Okay, so then I can in principle calculate. So this is my MBSC, this is my GW. If I take the difference, I can calculate the exciton binding energy, which is not possible. And even if you do it with a non-converged K point, you end up getting very large numbers which are not correct at all. And for bulk also, you can calculate it very clearly. So once you get the exciton binding energy, you can in principle calculate many other things. So this is okay. Now, for example, now just to add on that if you end up getting some system that you cannot really do either BSc or MBSc, then what you are supposed to do? So then there is another method that I was talking about a few minutes back. That's called one-year mod. So your exciton binding energy can be written as a function of this. This is reduced mass, this is Rydberg constant, and this is basically E effective. Now this E effective, you can calculate it from these expressions. So where if you are talking about only the contribution from the electrons, so the dielectric function takes care of this plot, you can calculate it from here. But if you are talking about dielectric function from the ion part, so then it takes care of here. So that way you can get a range. So that's called the lower range of the exciton binding energy and the higher range of exciton. That's how it is. But if you have this number from your experimental colleagues, so then it is very nice. You do not need to do it. You can straight away put it here and you can calculate that. If you assume that the excitons are 1 and 1. So this is what we did. So we calculated the upper bound and the lower bound. And if you see that it is in line with what you have predicted direct from MBSC approach. Okay, so the last part is calculating the other exciton parameters, especially the lifetime. So why we are doing it? Why we are? I mean, why 1 year mod? Even though it's giving you the exciton binding energy, but still it cannot give you the exciton lifetime, because if you want to calculate the lifetime, so you should have a peak like this, and then you need to calculate the FWH. So then you can directly calculate the lifetime of that exciton. Otherwise, you can also calculate it from this range separation from the wave function, so zero separation of electron and hole. If you take the inverse of this, so then you can calculate the exciton lifetime. So if you compare that, so this one is always following the same trend, irrespective whatever way you calculate your exciton lifetime. Okay, so then okay, let me. Okay, so this is also something important that we calculated the polaronic mobility from this simple model, and so we assume that we try to understand that okay, if there is an electron phonon coupling or not, and then we calculate it without electron phonon, and if you include electron phonon using Prolix model, so then you get these numbers, and you see that this polar mobility here and the polar mobility here are very different. That does mean there is quite a lot of effect because of the optical photons. So you cannot really ignore it. So that's what the idea is. Anyway, let me summarize the entire thing. So in the perovskite, I have talked about quite a lot of perovskites. So first we started with a simple lead halide iohybrid kind of perovskite. So these are the numbers. The problem of this is that we have a toxic lead. You want to get rid of lead, and that's why we switched to rubber perovskites. So things are okay. You could get rid of lead, that's fine, but that's not a very easy thing because the numbers are not at all good if compared to the conventional lead halide perovskites. Then we shifted to chalcogenide perovskites. Then also we could get rid of lead, but still the numbers are not good. But if you go to the Rudolphson-Proper phase of this chalcogenide perovskite, you see that the polar mobility is quite good compared to this. This is the exciton binding energies are also better than this, and the lifetime also is good, and also the electron proton coupling is not as high as you have in the other class. So that does mean that this type of material should be taken care of for the next generation of next generation materials for solar cell applications. And apart from that, these materials are also good these days as quantum materials also, because which people usually talk about Rashba splitting in strongly correlated materials, but we found that these materials are really very much sensitive for Rashba Dresselhaus kind of interactions also. So, but I do not want to talk about this. So with this, let me conclude. So I would like to thank my two former PhD students, Pooja particularly, who started doing this excited state in my group, and then Manish, who followed up, and the rest of the things done by Deepika. She is going to leave us next month. She is going to join Maxborn Institute in Germany, and all my rest of PhD students, and of course the funding agencies. Without them, nothing works. And thank you once again.
Thanks a lot for the nice talk. So now the floor is open for questions.
Yes.
Couple questions. You used an alpha before alpha in the HSC of 0.5. I think it was maybe DR3.
Yeah, it's too much.
Yeah. So
Yes.
So because after all, your active states over there are your lead states and your things. So those are very extended.
Exactly.
And usually for extended states, one uses a smaller alpha than 0.25.
I understand that, but we just wanted to see HSC overestimates. So you cannot fix it. I mean, in a very simpler way, you have to go to the GW and BSc to fix this quantum orbital and so on and so forth. We just wanted to see that if we can somehow reproduce it with HSC. So that's why we gave that extent where it is reproduced. But we do not really talk about that. You really need to do HSC with 50% enormously high alpha. It makes no sense. I mean, you do not need to go up to that.
No, I mean, when you did your GW, then could you not have started with HSC 0.25 or something like that?
Now, if you do that, then you cannot reproduce the experimental bandwidth because we are doing single search GW. So if you do SCGW, then the reviewer actually asked the same questions, and then we had to do SCGW. Yeah, no, we had to do the SCGW to validate that it works. If you do self-consistent GW, and that's how we validate.
And I have another question because one more thing in these materials is that because of the hydrogen bonding of the molecule with the cage, the orientation of the molecule is very important.
Correct.
So,
that affects in the band gap also.
Yes, that's right.
Yes.
Yeah.
So how it rotates basically, and sometimes.
So what is the orientation of the molecule in your crystal structure?
So which end? This peroxide?
MAPB.
Yeah. So that's actually it is kind of a disordered structure. So in the potential energy diagram, there are various possible states are possible where the orientations are somewhat like this, and they are all quasi-degenerate states. So what we did is that we saw that there are some experimental papers, and we tried to fix the orientation in such a way that reproduce the experimental pattern. So then we took.
You were reproducing the orthorhombic low temperature structure
Yes.
where these molecules are frozen in.
Yes, that's it exactly. Yes.
Are these calculations are done at room temperature or zero temperature?
Okay, that's a good question. So you cannot do it. You cannot call it room temperature because if I show it at the beginning, actually I did not talk about that. So let me explain you a bit to that slide. So this is what I talked at the beginning that so these are all these materials, right? So once you know the material from DFT or whatever you do, you get the total energy. But that has nothing to do with finite temperature. So if you want to address finite temperature, you have to calculate the free energy of formation. And that contains your translational, rotational, vibrational, spin, symmetry, many things. So if you take into account from usual statistical mechanics concept, so you can introduce those plus the DFT energy to capture whatever happening at a finite temperature. So what we did at the beginning, before talking about the electronic structure, that we computed all the free energy part and we ensured that these are stable configuration, and then we analyze the electronic structure. And that's why I made this this flow chart. So this is typically what we do, that if we do not have any idea of the structure, so this is the code that I have developed during my postdoc, and using that code I can to some extent get some idea that okay, what can be the, if I give you the X number of A atom, Y number of B atom, and Z number of C atom, what will be the global minimum structure, I can find out from there. So if we do not have any experimental input, then we do it. If we have experimental input, then it's very good. Then we compute the free energy using these methods, and then we can ensure that okay, these are the stable configurations. Once we know that, and then we do the electronic structure analysis.
So the electron thermal interaction that you showed for the polar return. So
that has a temperature factor in the Prolic Page-Polaron model. There is a temperature factor in there. So these are at 300 Kelvin.
So that is included in model.
Yes, that's already in the Page-Polaron model. So if you see there is a sine beta something like that, so there you have the expression of temperature. So this is computed for 300. But the material stability, the free energy is already computed.
But I do ask about the exciting stability at room temperature. If they persist,
so that's why you need to calculate the exciton lifetime. So if it is falling within the optimal region, then it is good. If it is not falling, if it is too low or too high, then it is not good for solar cell. So that's why you need to compute the exciton lifetime. And there are two ways that I showed. One is if you get the excitonic peak, you are lucky. But if you do not get the excitonic peak, then there are other indirect ways method by which you can calculate that. So in one way we did it using model PSC, because it could not do PSC for periodic very large system. But otherwise you can do it from this phi 0, that is basically the wave function of the electron hole with zero separations. You can calculate the square of this wave function and take inverse. That gives you indirect way of calculating the exciton.
Yeah, one more question there.
Was there a specific reason for introducing the organic molecule in the material?
Yeah, I mean, that's what exactly I wanted to make this fancy screen or something like that. I mean, that was the idea. Let me see. That's what I told at the beginning. Just a minute. So this is the starting of this IO hybrid world, because they wanted to make a synergy of the inorganic world versus the organic world. So the inorganic world is very stable, but it's very expensive. So we cannot afford it in our everyday life. But the organic world is very inexpensive, but it is not very stable. So if you can somehow make a material which is cheap but still very efficient like silicon, that's why people are trying for this inorganic organic hybrid materials. That's what I.
So like when we like take a combination of them, what is there any specific criteria when choosing the organic molecule?
Yes, because if you are talking about perovskites, so you have to talk about this Goldsmith tolerance factor and other tolerance factor. You have to ensure that these are, you cannot put anything at random. So that's what you have to take.
Theoretically, what are the challenges? Like LC and organic molecule.
These are all experimentally synthesized. I did not talk a single material that are not experimentally synthesized. During my PhD, I have done enough fictitious materials that are not ever realized anywhere. But here I have talked all the materials that are experimentally synthesized.
There are huge.
Yes, yes. Even Rudolph proper phase in IIT Delhi with Samit Sapta, we have synthesized this type of material. They are doing experiments on site, but they do not have the experimental technique to calculate exciton binding energy. So there they take help from us. That's very more sophisticated experiment, and it's not easily handled.
If we don't have further questions, then let's thank the speaker again.
Thank you very much.
Break for coffee for 15 minutes. If we come back, we at 5.
What time is the next?